research ideas and technical details. And I think please stay tuned for the second part. Second part, I will talk about what's next, and also involve some recent papers, and I think that's really promising about these topics. And maybe there will be more dense information about the topics. Yeah. Why I chose this topic? Actually, I started doing like real policy adaptation from my undergrad. That was like 5 years ago. I'm an undergraduate at Tsinghua University, and I was doing some autonomous driving research. And you can hardly see any PhD says he's or she's doing autonomous driving nowadays, right? So I turned to robotics. Yeah, and basically, I think the biggest reason is that sometimes I just feel frustrated since you can only. Sorry.
Is it working?
It might work, but it's somewhat strange, I think.
It's funny. Oh shit. Okay. Let me figure it out. I guess we continue.
Yeah. The most frustrated part is that I can only do some simulation-based experiments and evaluation. Since if you want to do some autonomous driving research or validation in the real world, it costs a lot. I think there's a test field in U Michigan that you can do some real car testing, and there's a Michigan City called. But for most of the labs doing autonomous driving, you can only do sort of things in the simulation. I can just find out there's no real world feedback, so there's somewhat frustrating, and so I move on to do the autonomous driving in the real world on an unmanned ground vehicle, and that was the first research I did in the Institute for AI Industrial Research in Tsinghua University, where I interned there for 4 years. And this work is how to do the sim to real. It's like we first close the vision gap. How to close that is to use the segmentation space. Since for the segmentation, it's just not relevant to what's alongside the road. And if there's an obstacle, we just don't care about what it is. Yeah. So segmentation space is a very canonical representation that can close the vision gap between the simulation and the real world. And we do a lot of domain randomization about dynamics and scenario in the color simulation, and then we test the results in the real world, in the Tsinghua campus, and also in Haoyi driving school. Though Tsinghua and Haoyi driving school both in Haoyi district in Beijing, but if you live in Beijing, it's like Haoyi district is really big, and commuting back and forth takes 3 to 4 hours. So it's really, and we did these experiments in the summer, so it's very hot. In Beijing, it's though it's a northern China city, but in the summer it's very hot and dry. So it's just like the sunshine shed on your skin. It's just like someone using the needle to attack you. So it's really yeah. And then I just turned to some indoor robotic tasks, partially because of this reason. Yeah. But I think the most largest reason is that I find something that I can delve into to investigate in principle how to close those domain gaps. Instead of just doing some domain randomization and doing some very simple canonical mapping. Yeah. So the first work is about window tracer simulator, and it's basically about how to close the dynamics gap. So there's friction, there's gravity, there's a lot of physical properties that you can do domain randomization too, but if you just do the memorization, there will be huge parameter space, and it's always hard, and it takes lots of engineering to do so. So this paper is about how to find out where the domain gaps are large and where the domain gaps are small, so that we can leverage more simulation data on those areas with a small dynamic gap. Yeah, so for visual gap, it's like there are lots of mature methods that we can do, like to train a robust and transferable encoder, or just use some proper model setup, like use the segmentation model. But for the dynamic gap, it's like it causes a very systematic bias and widely exists, no matter it's a vision-based task or not. So it's not easy to address. Yeah, so for reinforcement learning, we normally have two directions. The first direction is using the imperfect simulator to do the online reinforcement learning, but the simulator always involves some dynamic gap. So you need to do like sim-to-real policy transfer to the real world. And another way is to directly circumvent the simulation part. Is using some offline real-world data and do the offline reinforcement learning, but it suffers from limited coverage since you cannot collect too much data from the real world. Yeah. So the basic idea is to combine the online and offline reinforcement learning under this dynamic gap. So yeah, so we have the question: how about combining the limited real data and the real in offline RL and unrestricted exploration through the imperfect simulation in online RL? They can complement each other. Yeah, there will be some math. So if you know reinforcement learning, there's a standard way of how to do policy violations using the Bellman update, the Bellman error. But here we add a value regularization term. How to interpret this? The first term is to minimize the dynamic gap weighted self maximum of the Q values. That's just to push down the Q values on those high dynamic gap samples. And the second term is to pull out the Q values on the trustworthy real-world offline samples. Yeah. So there is a weight about the dynamic gap. So that involves another question: how to do the dynamic gap quantification? Is the omega. Yeah. Here, so we normalize the U, the dynamic gap, into the dynamic gap distribution omega, and define the dynamic gap U with the KL divergence between the simulation dynamics and the real-world dynamics. And according to the Bayes rule, we can derive the final form of this. And you can just estimate this weight with two discriminators, DSAX and DSA. So DSA tells what is the probability that this state action packet comes from the real world. And the state action and the DSAX just tells what's the probability that the state action S prime, the translation comes from the real world. And then also the Bellman error also need to adjust, since it learns from both offline data and the online simulated samples. Yeah. And so here we need to reweight the density, since we sample from the simulation. So the dynamics are wrong. So we have to add a weight on it. And this way they can just reuse the result that we estimated from the discriminators. So that's the basic idea of H2O. And this is just not to perform conservatism, it's to perform adaptation, since if you look at these areas, there is a very limited offline data, and the dynamic gap are relatively large. So this is the dynamic gap. This is the offline data distribution. So if this one is really small and this one is really large, then it will perform the conservatism. Yeah. But in this area, there's lots of offline data, and the dynamic gap are relatively small. So it will perform optimism. So we should involve lots of simulation samples here, since there's nothing to care. Yeah. And there's some real-world validation. We implemented on the well-landed robot, and the first task is about standing still. And we compare with the offline RL SAC and the offline RL CQL and some cross-domain RL dark and dark class. And you will find that only the offline RL method CQL can be comparable with our method. But it can only stand still for 11 seconds and bump into the ground. But our method can last to 35 seconds and more. Yeah. And for the next task is about moving straight. And we can also find out that CQL is more comparable baseline. That's the offline RL method, but it's more shaky, and the body angle just changes a very large range. And also, you can find that the CQL velocity is doubling the target velocity. But H2O can just follow the target velocity accurately. Okay, thanks. It's okay, I think. It works. Yeah. I should allow it. It works. It works? Yeah. So, and this part cloud just show that sim-to-real is very necessary. Since if you just evaluate the SAC algorithm that trained in the simulation, you will find out that in the simulation evaluation, SAC can obtain a very high reward, and it's even higher than H2O in the simulation. But in the real world validation, the case is just opposite, and the SAC algorithm totally fails. But you can find that H2O can obtain higher reward than it does in the simulation.
But do you have any intuition why SAC completely failed?
Yeah, since there's no anything to real design, and SAC only adopt the online interactions in the simulation, and there's no offline data accessed during the training of SAC.
I see.
Yeah. So simulation-based evaluation can be sometimes very misleading due to the scale. And there's improved work of H2O, and that's more like towards the reinforcement learning side. Yeah, so H2O has some drawback. It adopts a very over-conservatism. It adopts a very over-conservative bytecode. It underestimates some values before making further progress, and it's just inflexible to this type with recent very strong offline RL and online RL methods. And it's also very inflexible since there's no exploration design that can be introduced. It's a very conservative bytecode. Yeah, and the dynamic scale quantification also involves lots of approximation since the explicit dynamic scale is sometimes unreliable in many real-world situations. So the motivation for this work is to move on and develop H2O to a more flexible and less conservative framework. Let's first revisit offline and online RL in a very unified behavior regularized manner. So we can frame the offline RL and online RL with this. And we can find that offline RL is always regularized policy to a behavior policy in the offline data set. That's the new. And online reinforcement learning, it just regularizes the behavior to the entropy. So it wants more exploration, right? So how can we just unify this two paradigm and construct a mixed Bellman update with the Bellman target of offline RL and online RL. Yeah. And then we can use this mixed value update method to do the Bellman update and also adopt the H2O weighting here. So H2O plus is the mixed value update and the dynamics reweighting. And it's just manually regulates the value learning with single value from the offline data. So it removes the excessive conservatism from the offline learning like CQL. And the second is it allows for active exploration. So you can do any exploration design here, and it will transfer to the Bellman update of the online learning. And third is it can offer the flexibility to accommodate various strong paradigms in offline and online RL. So you can also change the term or change the app function here to adopt more advanced offline reinforcement learning methods. And the fourth one is it removes the need to estimate the explicit dynamic gap, since that involves lots of approximation. And I think the real experiment is quite similar with the H2O one, and I want to highlight this figure. You can see H2O can explore in a wider range, and it can explore some very high rewarding region other than the H2 for policy learning. And there is also some other works that learn different discriminators, mappings between the two domains or something else. They are too complicated and inflexible. So it just reminds us if we can do the cross-domain techniques at the data level, why not bridge the domain gaps at the data level instead of the policy level? If we can do so, there will be a more generic and flexible and fundamental solution. First of all, it's a task agnostic, so it can apply to any policy learning algorithm downstream, since we only do it in the data level. So you can choose whatever you want to train your policy. And the second one is modality agnostic. So if the observation is a point cloud or image, you can apply any observation encoded to it. And the third one is domain agnostic. So it's fine-tuning free for any available source domain. You don't have to construct mappings between every source and target domain pairs. And the fourth one is orthogonal to any other cross-domain policy adaptation method. So you can first apply the data adaptation method to your data, and then if the domain gaps are not totally eliminated, you can also add other cross-domain policy adaptation to complement. So how to achieve this? Here we draw an analogy to diffusion-based transfer in computer vision. So there's a very famous work called SD-edit, and you can, if you learn diffusion prior in the photorealistic distribution, and you can use the diffusion editing method to transfer a stroke-painted castle into a photorealistic one. That is like perturbed with SD means adding some noise, but only add partial noise in the diffusion process, and then you do partial denoising. So it will drag the sample back to the photorealistic distribution. So it just reminds us what if we do this similar thing to trajectory editing. Can it also create domain gaps rather than some primitive information and across the embodiment and the domain gaps at the data level? But before that, we need to consider the difference between image editing and trajectory editing. Image editing is like it only consider about the spatial representations, and it treats every pixel homogeneously in the spatial modeling. But the trajectory editing is like it involves a different modality like state, action, and reward. They all present dissimilar notions, and they have a very complex like dynamics or correlations within them. So it's a lot more complicated. here's the architecture for the diffusion transformer. We first do some separate encoding and decoding for the action, state, and reward like separately. Why to do this? Since we want to first capture the self-consistency within the same modality, so that then we can do some other like cross-attending for the state, action, and reward. Since that would be called late fusion. And after that, we just cross-attend the state and action with each other and use the output of the state action, concatenate it together, and cross-attend with the reward. That just I think, clearly capture the dynamics dependencies among the state action and reward. So why just not also cross-attend the reward and the state action with each other? Why just do it in one way? Since the reward is a function of state action, but state action are not the reward for another function of reward. So it just captures some very clear dynamic dependency. And you can also add some flexible condition, like you can add the return as a condition, so that it can steer the diffusion acting process towards the higher rewarding regions. Yeah, so that's the first time I show some very boring simulation benchmark. There's actually also simulation results in the H2O and the H2O plus paper, but I didn't show them. That's enough. For instead, we do some. We first do some preliminary validation in the simulation, and in the Bojoku benchmark, we just change some dynamics and the embodiment, like the time size and friction and gravity, to make the source domain, and we use the original environment as the target domain. And then we can find that if we add the target data with the source data edited with XTAD, we can learn very performant policy. But if you just add the target data, augment the target data with the original source data, sometimes it will result in some very insignificant, in some very significant performance degradation. And then the real world validation. Our target domain is airboat, and the source domain is a VLX robot. And we do the trajectory editing in the latent space, since it is somewhat very hard to do the editing in the original linear space. Yeah, so we do it in the latent space here. And you can find the red bar is the policy trained on targeted and edited source data, and it performs very well. But you can find that in the real world, the blue bars are just adding the target data with the original source data. Sometimes the success rate is 0. It cannot even comparable to the gray bar, which we only use the target data as a training data. Yeah. So for experiments with only 2 embodiment, I think the result is very significant. But how can we scale it to 10 or 50 or even 100 embodiments? Can this still work? It's an open question, and maybe we have to scale it up. I think I may skip here.
So how large you change the environment so that you combine it together, it doesn't work?
No, just the embodiment change. And the camera position and the pose are slightly changed.
So just a small change will reduce the...
Yes, and it might not be that small. Yeah, since the embodiment also influence a lot. Yeah. Yeah, so let's move to the second part. It's about what's next. From adaptation to self-adaptation. It's like previous work I just mentioned all about adaptation. That means we have a target, right? But I think the final solution or the final form of robotics will be always self-adapting. You're going to very new or different tasks and domains. you have to figure out by yourself how to like improve step by step. Yeah. So for adaptation, it's like the first point is just what I mentioned in H2O. So maybe some better domain gaps quantification method is needed if you are only like working around with some local motion task and there's only a dynamics gap, and do the domain gap quantification is relatively easy. Yeah. And the second part is make an RL great idea. Yeah. Like better reinforcement learning recipe for foundation policy fine-tuning should be developed. And there is an example. I'm not sure why. I'm not sure whether they solve all the things, but it's really a very good recipe, since it just stacks all the, I think all the very useful ingredients together and make it work. That's an RL token by Physical Intelligence. It's just released in last month, and it just want to bootstrap the online reinforcement learning with the vision language action model, and it just include the representation of the vision language action model into a relatively small latent space called RL token, and use the RL token to scale for the downstream online reinforcement learning paradigm. Yeah. I think there are some key hot take. The first one is that they are using the residual action refinement. That's not just like those standard residual learning. Standard residual learning is that we learn a residual network that only output the delta action. Yeah, but they do it with the input the original action from the vision language action model and output the action plus the delta action together. Yeah. So they said the reason is that the vision language action model are always multimodal. And if there's a true solution given by the vision language action model, one is to the left, one is to the right. If you only learn the residual network output the delta action, it just don't know to add this delta action to which actions, to the left or to the right. So it will be hard to like for the residual network. So they just refine the residual learning with such a paradigm. With the input is the vision language action output, and output the action and the delta action together. Yeah. And the second is they do the action chunking queue, since it's a very I think it's a very useful trick to stabilize the value learning if there's lots of process manipulation and you need to learn a smoother Q value. And the third one is the human intervention. It's also adopted in Pi 0.6 star. Yeah, that's when the online replay by the robots fails somewhere, you can just add the human intervention to help it correct and to guarantee the quality of the data collection. And the fourth one, maybe somewhat surprised to me, that's using the TD3 plus BC algorithm in this recipe. Since TD3 is off-policy online reinforcement learning, and it's very popular. And TD3 plus BC is an offline reinforcement learning method. So why use an offline reinforcement learning method in such an online reinforcement learning recipe? Yeah, it's that if we dive into why TD3 plus BC work in offline RL, we can find that the BC is a regularization about the learning policy with the behavior policy in the offline data. So they also need this because they don't want the policy to deviate too much from the vision language action output. So there is a behavior cloning term to regularize the learning policy to not deviate too much from the vision language action actions. Yeah, and maybe more existing method will be found useful for the recipe, and this will be like enriched more and more. Yeah. And the second part is about the reward angle. That's what I'm working on. Yeah, that's to like use a training-free reward fine-tuning method for better policy fine-tuning. Since if you just do policy fine-tuning, it's very limited by two aspects. The first is the base policy performance. That's what we cannot change. And the second one, the last one is the reward model, or the reward function, or the reward values. And if we can just, we can not only adopt a sparse reward to achieve everything. And there are some very dense reward from some vision language models or some vision foundation models. They are just not control aware. They are just matching with the pixels. They just matching with the pixel level features. They are not control grounded. So how to use a training-free recipe to merge the such a dense reward with the binary success or failure reward together will be, I think, a very interesting topic to achieve better policy fine-tuning performance. Yeah. I think the next keyword is active, to do active learning. So active always means some sort of guidance. So how to guide? It's like if we want to actively learn something, that's because we know we need to learn it. But for the robotic policy learning, it's like they just don't know how to improve itself. They can only improve itself according to the data that the human provided, right? So we should introduce some privileged information here. So the privileged information will involve some model that know more than the policy does. Maybe some more advanced vision foundation encoder and maybe tactile sensing or something. And there's an example. This paper is called real-world reinforcement learning of active perception behaviors. When they are trained the critic, they just involve a very advanced vision encoder. I forgot the name. That is to do the bounding box about the target object. That's a duck. So if it learns the critic with such privileged information, it will do some very it will just do some very surprising search or exploration during the test time. Since if they do the bounding box during training the critic, it's like this vision model can recognize this is a duck when only the duck head appears in the camera, in the image. So the critic will always reward the policy that do some search or exploration. For example, there is a duck behind my laptop, and if the initial condition is like here, it's like there is no duck in the camera. But the critic will always reward some actions that do some searching about if there is a duck behind the laptop. That's what the privileged information make it. Yeah. Information. I think the information should also be invariant. For example, if we hold an apple or hold an pear, if we learn a vision policy, it's like it will probably act differently because it sees apple and pear, they're different. But if we use the tactile sensing, it's like the tactile information about an apple holding up and or a pear holding up and it's quite similar. Then it will do the same action. So we should find out some policy environment perception. And here's a naive simple. There's a naive example. There is a paper from RSS 2022, and their idea is to swing the rope to reach a target to reach a target point, and refine its action test time to minimize the distance between the goal state, the goal point and the rope. So it can first train the simulation, first train the policy in the simulation to learn how to approach the goal step by step. And it will just transfer this skill, this very high-level skill to the real world. It's very interesting, right? But it's somewhat tricky since the distance between the goal point and the road is achievable. It's very achievable. But in many real-world tasks that we do in the 3D world it's very hard to find such an invariant information or invariant perception. And the last keyword I think is context. There's very popular paper in the best paper final. I think it's the best paper or the best paper finalist in Corel last year. It's called Locoformer. Skill the edge of the training massive embodiments in the simulation and use a very large transformer to do the in-context learning. It's like they just add different episodes of different embodiments into the input, and it just distills some very high-level knowledge about how the policy recover from failure to the success when it was adopted in a new embodiment. But it involves 100,000 embodiment tasks and 500 times than the specialized policy. That costs a lot, and it's relatively easy for locomotion since in locomotion you can adopt the simulation, since there's only the ground that you have to interact with. But for manipulation, it's like much harder since you have to interact with lots of furniture, lots of stuff in the real world. So how to make a reasonable long context, like how to structure efficient content for manipulation is a very key question and open question in the promising field. And I also don't think that we should use in-context learning for manipulation just as what we did in local format. Since in local format, it can just recover from the total failure. But if for a manipulation task, if it just starts from total failure, it's like it will, there will be two scenarios. The first scenario is like it will just sweep out all the things on the tabletop. It just randomly acts. And the second scenario is it just stuck, since it don't know how to do. And there's no variable context collected. So for manipulation, there will be I think the content should serve as an effective activator for the foundation policy during the pre-training phases, so that the foundation policy, when we deploy the foundation policy in a new environment, it has a relatively safe performance for some basic skills, so that you can collect some valuable context. Otherwise, it cannot work. Yeah. So thanks for listening, and if there's some question, feel free to ask. Yeah, thanks.
You mentioned active learning. There's like two camps in there right now. One is that you put the guidance in from the other model, right? From like let's say a frontier model, and you then take it out for the learning, because the challenge then becomes, it learns in RL to use the guided instructions, but how does it then know how to do it when you take the guided instructions out? I'm just curious if you go deeper into that, and what are your thoughts? Like, there's one option of just taking it out, and the other option is like doing some sort of continued pre-training to still learn, with it in, and because I'm very bullish on guided learning and active guided learning being a good solution, but there's an open question there that
it's like the actor just distills some privileged information from the guided, so that will work. Right.
But then like often the model may just learn to use the privileged information, and if it doesn't get the privileged information in production, it doesn't know how to do the next task.
So you have to, in the pre-training phase, you have to utilize some privileged model like vision language model or some vision foundation model all the time, since they have seen lots of things, right? So there's no free lunch. Just like I also agree that during the pre-training for the word model or word action model, you need some data, even there's no behaviors or manipulation behaviors inside. Yeah, since since they just involve lots of privileged information or additional information that you can use downstream, right? But if you didn't adopt them, there will be no guidance and no active learning.
So my question is on, if you remember at the end you had TD3 plus BC for iceberg, right? And I mean, based on my experience, whenever I try to do some regularization using view cloning, it either ends up being very brittle or just limiting the final performance of the model. So do you have any insights on that?
I think leveraging behavior cloning when you want to draw the policy, not deviate too much from a reference policy, is good. It's good. Since I think behavior cloning cannot make the policy brittle. Otherwise, it just give a very it just give a reference. And if you don't want to since reinforcement learning has lots of exploration or something, and it will just deviate too much from what you desire. So if in offline reinforcement learning, you have to fix the policy, not deviate too much from the basic policy in the offline data, and so that they adopt such a philosophy in the RL token world. That's to regularize the policy with a vision language action model. Yeah.
I mean, I think brittle in a sense that it becomes very sensitive to the regularization coefficient. And for example, if you remember in their paper, they have many tasks they have a few tasks which gets to 100% almost. And there are a couple of tasks which got started around 80%, 70%. I was wondering if that underperformance is due to because of regularization?
You mean the underperformance in which task in this paper?
I think in this paper, there are a couple of tasks which doesn't go to 100%, right? Because of the nature of the task. Do you think it will go away if you just let it run for another 10 hours? Or it will never be able to go up to 100 because of the BC regularization?
If there is no BC term, of course, it might collapse. Yeah. But with BC, it's more sample efficient, since it has always has a reference to follow. Yeah, so it will be more sample efficient. Yeah. Any question?
For the H2O plus, did you also try having a pre-trained model
No.
offline so that it could be a little bit more?
There are some old works, so there's no pre-training this word.
Yeah, it's completely from scratch. Regularization.
And our next my ongoing project about reward is using a base policy model, and we try to figure out how to do the policy fine-tuning for a base foundation policy model.
Okay, so that actually brings to the next question. You also mentioned for the policy fine-tuning, it's also based on the base model's performance as well. So that's anyways a limitation for one of the axes. You mentioned that the reward, there is one limitation based on the reward, and then there is one limitation based on the base policy kind of fine-tuning.
Yeah, that's so sure. That's not a stream from scratch. Yeah. That's how to do the fast adaptation based on the foundation policy. And use the reward fine-tuning to achieve better policy fine-tuning performance. So please stay tuned. Maybe it will come out next month or so.